Good morning everyone. Welcome to the lecture series of the subject name VLSI technology with the subject code KEC 053 as per AKTU syllabus scheme. This subject is dedicated to the fabrication steps, which are used to for the formation of any IC, right. So in the previous lecture we have seen the with the help of photolithography process we have created one window, and over that window we have to diffuse some of the dopants, right. And after that when we created the window where we have to dope the dopants, then with the help of etching process we have removed the silicon dioxide so that we can come in contact with the silicon wafer, where we have to diffuse some dopants. Now before diffusion we have to deposit some of the material over the substrate which is used as a further which is used for the further processing steps. So this lecture, this is the 18th lecture, and it is dedicated to the process of deposition. So what basically deposition is and what is the need of this deposition process? The deposition in general means we have to deposit some of the material over silicon dioxide, right. So this material, it can be polycrystalline silicon dioxide or silicon nitride. So the film of various materials that are used in VLSI or ULSI technology, and addition to being part of the active devices, this deposited thin films provide the conducting regions. So the very first point is they provide the conducting region within a device. They provide the electrical insulation between the materials and protection from the environment. So depending upon the application, for which application we are using which material, we can have different types of materials, right. For conducting regions, for electrical isolation. For electrical isolation, as you know, if you have studied this CMOS design, we have this N+ doping, which we will cover in the upcoming classes. This is the p-type substrate, right, and here we have the silicon dioxide layer, right. Over this we use polysilicon as a gate material. Okay, so this material is used as a gate material particularly. So this we are going to deposit in this lecture. So so the very most widely used thin film microelectronics are your polycrystalline silicon, which is commonly known as polysilicon, or it is also sometimes written as here poly and silicon. Doped or undoped silicon dioxide, stoichiometric or plasma deposited silicon nitride. The silicon dioxide, the polysilicon serves as a gate electrode material for the MOS devices. Here I have shown you that this gate, where we have to apply some gate voltage, this material is made up of polysilicon always. The conducting materials used for the multi-level metallization. Multi-level metallization means because we are using n number of transistor, millions and billion numbers of transistor we are using in VLSI and ULSI technology. So it is not possible to wire the complete circuit with limited number of wires. So these days we are working on 7 to 8 to 9, I think up to 9 metallization layers. So that is this is known as metallization, multi-level metallization, and the metallization is done in such a way that first level is done in a horizontal way, then the second layer will be done in a vertical way, then third layer again horizontal, fourth layer again vertical way. So this way we generally do the multi-level metallization. Next, your polysilicon material, it uses a contact material for the devices with shallow junction. This polysilicon, it can be doped or undoped. It can be doped or undoped with the elements such as we can dope the silicon polysilicon with arsenic, phosphorus or boron, and this doping is done to reduce the resistivity. To change the resistivity of the polysilicon, we can do the doping, and the dopants can be incorporated in situ during the deposition and later by the diffusion or ion implantation. This doping can be done. And this polysilicon consists of several percentage of oxygen in the semi-insulating material for the which is used for a circuit passivation. Next, for the dielectric material, when this polysilicon is used as a dielectric material, it behaves as a insulating material between conducting layers. Okay, diffusion and ion implantation, where we are going to use the diffusion and ion implantation marks. So there we can use these materials as a layer. Then for the diffusion sources, where we have to dope some oxides, then capping dope film to prevent the dopant loss. When we dope some type of material, okay, when we dope some type of material, sometimes we cap this dopant area, so that these impurities are not lost in the upcoming processes. So that is known as capping of dope films. Then getting impurities, passivation to protect the devices from the impurities, from the moisture or scratches. So for all these purpose, the phosphorus doped silicon dioxide, which is commonly referred as P glass. This phosphorus doped silicon dioxide is also known as P glass, or it is also known as phosphosilicate glass, PSG. It is very much famous as PSG, and especially used as a passivation layer, because it exhibits the diffusion of impurities such as sodium, and it softens and allows the flow from the 950 to 1100 degrees C. Okay, from 950 degree C to 1150 degree C, to it will help to create a very much smooth topology, which is beneficial for the deposition process. The next material used in this category is the BPSG. BPSG is your boron phosphosilicate glass. It is formed by incorporating both boron and phosphorus, right? The name indicates boron and phosphorus. So it is formed by the incorporating both the impurities, that is your boron and phosphorus, into the glass, which flows even at the lower temperature. Your previous material PSG is used at from 950 to 1100 degrees C. This material allows at the temperature range 850 to 950 degrees C, and the smaller phosphorus content in the BPSG reduce the complexity of the aluminum corrosion in the presence of moisture. Okay, so this will also help to reduce the corrosion possibility. Silicon nitride is sometimes used. The next material, silicon nitride, is used as a barrier for the sodium diffusion. It is used mainly to block the moisture, and it has a very much low oxidation rate, right? So if you use the silicon nitride as a barrier, you can easily control the oxidation process, so that unnecessary oxidation should not be carried out at any level of fabrication step, because we know that in any furnace your oxygen will be there. So to protect the device from that oxygen particles, we have to use the silicon nitride layer. The next is the low cost, that is named as local oxidation of silicon process. It is also used, this also uses silicon nitride as a mask. The patterned silicon nitride will prevent the underlying silicon from the oxygen, but leaves the unexposed silicon to the oxidized, right? So wherever we have deposited the silicon nitride, underneath that layer, your silicon will be protected from the oxygen particles, and unnecessary oxidation process will not be there. And where it is not protecting the layer, only that area will be oxidized. Silicon nitride is also used as a dielectric for DRAM, that is your dynamic RAM, MOS capacitors, where it combines with the silicon dioxide. Now, what are the methods used for this deposition process? The very first method used for this deposition process is your physical vapor deposition. It is also known as PVD. In case of physical vapor deposition process, this technology falls into two category. Evaporation is one of the oldest technique that is used for the depositing thin materials. Okay, so evaporation, where if you have some material, evaporate that material up to a certain temperature, and that material will be allowed to condense. So that process is known as your simple physical evaporation. So it is one of the oldest technique which is used for the deposition of your thin film. A vapor is first generated by evaporating a source material in a vacuum chamber, and then they are transported from the source to the substrate and condense to a solid form at the substrate surface. The second thing is the sputtering. The sputtering involves the ejection of surface atoms from the electrode surface by the momentum transfer from the bombarding ion to the electrodes. Okay, some electrodes will be there that are used to bombard the electrons to the surface. The generated vapors of electrode material is then doped on the substrate surface, same as the evaporation. Almost same thing is done, but they in here very high speed ions are bombarded to the wafer surface. So this process is very much controlled and generally applicable to all the materials, such as where the materials work as a semiconductor or insulator or some alloy. Okay, so this is the basically sputtering diagram. The sputtering diagram, here we can see that it is a complete chamber where you have some gas supply from this side. Some cooling and heating materials will be there. Right here we have the coil, which is used to some RF coil, which is used to heat up the substrate, and another terminal will be connected to DC or RF supply or some ground. Some cooling particles will be used to cool down the substrate. Here we have the substrate will be light here. Okay, this is the shutter. The target will be taken from here. This is the target. Here we have applied some DC and RF voltage. So this cooling shields allow to maintain the temperature in the furnace. So this complete process is carried out in a vacuum chamber, and some mechanical pump, gyro pumps, isolating valves are used, so that this process it is used to maintain at a very high vacuum. So this very high vacuum is created with the help of some mechanical pumps and gyro pumps. Normally shear simple pumps are not used in this process because they have some oil particles, and oil particles are not at all welcomed in the process. So so these gyro pumps and some high level mechanical pumps are used in this process. So the next process under this deposition is your chemical vapor deposition. It is a very much important process. This process can be classified as atmospheric pressure chemical vapor deposition, named as APCVD, then LPCVD, which is abbreviated as low pressure chemical vapor deposition, and PECVD, that is your plasma enhanced chemical vapor deposition. Okay, as the name indicated, it is generally carried out at some atmospheric pressure, and here this process will be carried out at slightly low pressure as compared to your atmospheric pressure. And in case of plasma enhanced CVD, some plasma will be used for the deposition of the material. So if you compare the two techniques, APCVD and LPCVD, it shows that the benefits of low pressure deposition process it will have the uniform step coverage, precise control of composition, structure, low temperature process. It is a very much low temperature process. High enough deposition rate can be achieved, the throughput will be high, and the low processing cost will be there. Okay, so these are the some advantages of APCVD. These are the some advantages. Okay, these are the some advantages of APCVD. And furthermore, if no carrier gases are required in LPCVD, the particle contamination will be less. The most serious disadvantage of LPCVD and APCVD is that the operating temperature is high, and in case of PECVD, it is an appropriate method to solve all these problems, where your temperature will be low and contamination will be less in case of PECVD, plasma enhanced chemical vapor deposition. So, if you compare the advantages, disadvantages and application, your APCVD, it is generally carried out at low temperature. Very much simple reactor is used, fast deposition process will be there, and it will be carried out at low temperature. The major drawback is some poor step coverage, particle contamination will be there. This poor step coverage is as compared to LPCVD. Okay, it has a very low throughput, and it can be used for the doped and undoped oxides, for the formation of doped or undoped oxides. Next, we have the low pressure chemical vapor deposition. It has excellent purity. It will provide uniformity throughout the deposition process. Conformal step coverage will be there. Large wafer capacities can be handled, and it will have a very high throughput. It is generally carried out at a high temperature, and the deposition rates are low. So, the deposition rate as compared to your atmospheric pressure CVD, it has a very low deposition rate, and generally it is used for the doped and undoped oxide material, silicon nitride, polysilicon, tungsten and tungsten silicide. Okay. So, for the deposition of all these materials, we generally prefer to have LPCVD process. So, whenever your question is asked in the exam that explain the deposition steps which are used for the polysilicon material or tungsten. So, beside that, the reaction which are carried out in the deposition process, we can draw the reactors which are used in the process also. Then we have the plasma enhanced CVD. In case of plasma enhanced CVD, it is carried out at low temperature, fast deposition rate will be there, good step coverage we are going to have. The chemicals such as hydrogen and other particle contamination will be there, but they are of small amount. It is used for the passivation of nitrides, with the help of which is done with the help of nitride. Low temperature process is used. Insulators over materials we are going to use deposit with the help of PECVD process. The insulating means where we have to where these materials have to behave as a insulator. Next, the equipments and the reactors which are used. The design and the operation of these CVD reactors depends upon the various factors. One way of grouping the CVD reactor depending upon the method used to heating the wafer. So, the first method is the which way we are going to heat the wafer, and the another criteria is the pressure regime operation, that whether it is working on atmospheric pressure or it is working on reduced pressure, that is your low pressure, right. So, depending upon that, your equipments can be classified. Reduced pressure group can be further split into low pressure CVD reactor, in which your energy is entirely thermal, as well as the plasma enhanced CVD reactor. So, generally 4 types of methods are used for the wafer heating. The first one is the resistance heating, then we have the RF induction heating, then heating is done by energy from the glow discharge, that is named as plasma. We have seen in the previous classes that how the plasma is created when your gases are charged under a very low pressure. A very glow discharge will be there, that is known as plasma. Then it is done by then the wafer heating can also be done by heating by proton energy. Okay, so these energy can transfer either to the reactant gases or substrate. So when the radiant heating from the resistance heating is done, the coil surrounding the reaction tube, it is utilized, not only the wafer but also the reaction chamber will become hot. So, these kind of designs are termed as hot wall reactors. Okay. So, in these systems, the film formation occurs both on the substrate and on the chamber wall. Okay, so your wafer is also hot, and the chamber walls are also hot. Complete system is hot. So when we deposit some material, that deposition will be done on the wafer, as well as some of the material will be deposited on the wall chamber. So that time that we have the drawback. Next next is so to avoid this, the frequent cleaning is used to avoid the particle contamination. On the other side, energy input via RF induction or infrared lamps mounted within the reactor only heats the wafer as well as the susceptors, but do not cause the excess heating to the chamber. These kind of chambers are known as cold wall reactors. So for high volume production, the number of wafers produced per batch should be large as large as possible. So this lead to the development of hot wall low pressure CVD reactors, which we are going to see in the upcoming slides. For the maximum wafer capacity, the wafer held vertically perpendicular to the gas flow in the quartz tubes. So here we have seen that we have this chamber. Your wafers are placed vertically so that more wafers can be processed simultaneously. Okay, and here they are placed on a susceptor. It is placed inside a 3-zone resistance heating furnace. Right, some vacuum pumps will be there to create the vacuum inside the chamber, and source gases are provided. Before starting any process, we can also provide the inert gases which will control the unnecessary contamination particles. Okay, so vertically we are going to place the wafers. The pressure is typically between 0.1 to 5 torr. The temperature range for this reactor is between 300 to 900 degrees C, and the gas flow rate is between 100 to 1000 standard centimeter cube per minute. The large load space will be there, good uniformity will be there, and the ability of feed large diameter wafers are there. These are the major advantages of this type of reactor. The drawback is the deposition rate will be low. It frequently use some gases which can cause practical problems. Okay, so this is the commercially hot wall reactor, low pressure reactor, which is used for the deposition of polysilicon. Next we have the atmospheric pressure CVD reactor, which is used in the microelectronics industry. The operation at atmospheric pressure keeps the reactor design simple, and it allows the very high deposition rate. However, the technique is susceptible to the gas phase reactions, and the films typically exhibit a poor step coverage. Since APCVD is generally conducted in a mass transported limited regime, the reactant flux to all part of every substrate in the reactor must be precisely controlled. So these are the some diagrams of APCVD reactors. Here we can see it is we have the horizontally, these wafers are placed horizontally. It is not exactly horizontally, some they are placed with some angle, and from here we have some gas flow. It will be flow like this, and exhaust gases will be taken out from here. The second is the continuous process APCVD. In case of continuous process APCVD, we have this film. Okay, we have this susceptor. It is placed on a conveyor belt. Okay, some conveyor belt will be there. It is placed on a conveyor belt, and some wafers will be placed here. Okay, and they are in a moving position. Okay, so here from here we have this inert separator gas and the second reactant gas. The first reactant gas will be passed from this side, second gas will be passed from this side, and we know that inert gases are used to control the involvement of contamination particles, right? Your inert gases, argon or something like that are used inside the reactant, so that the oxygen particles they do not react with the substrate, and they do not form the oxide layers, unnecessary oxide layers, right? So some other they are also used to control the contamination particles. The next is the platinum type continuous processor AKGEC reactor. In this case, we have this conveyor belt. Your heater will be placed inside that. Here we have the wafers which are placed over that. So here we have the wafers. Okay, platinum. Your gases, reactant gases will be passed from here. Okay, so this way we can also use here as first gas, second reactant gas. Okay, depending upon the requirement, and we can have the inert gases also include. Okay, inert gases can also be included in this, right? So this way these reactors work. Next we have the PECVD system that shows rather relying solely on the thermal energy to sustain the chemical reaction. PECVD system uses an RF induced glow discharge to heat up the system. The energy will be transferred into the reactant gases and allowing the substrate to remain at low temperature as compared to your APCVD and LPCVD process. In case of plasma enhanced chemical vapor deposition, it allows the deposition of film on the substrate that do not have the thermal stability. Okay. In addition to PECVD, it can be enhanced the deposition rate as compared to with thermal reactions alone. It can produce the film of unique compositions, and the properties of that unique compositions can be maintained. However, the limited capacity we are going to handle the limited capacity wafer in this kind of reactor chambers, and especially the large diameter wafers can be handled, and the possibility of particle contamination by loosely adhering deposit may be the major concern, because your deposition rate your deposition gases are in the particle form, right, in the gaseous form, right. So they will be moving inside the chamber. Some will get pasted on the substrate, and some will be loosely and they are free to move. So that may create some concern in this deposition process. So with regard to this PECVD reactor, there are generally three types of reactor. First one is the parallel plate, then we have the horizontal tube, and we have the single wafer. In case of parallel plate reactor, the electrode spacing is typically 5 to 10 centimeter, and the operating pressure range is 0.1 to 5 torr. In spite of the simplicity, this parallel plate system suffers from a low throughput. The drawback is it has a low throughput for the large diameters. When we use large diameter, the throughput will be less. Moreover, particulates flaking off from the walls or from the upper electrode can fall horizontally positions wafer, right. So horizontal PECVD reactors resembles a hot wall LPCVD reactor, consists of a long horizontal quartz tube that is radiantly heated. So especially long rectangular graphite plates serve both as an electrode to establish the plasma and to hold the wafer. So a single plate can be used as an electrode and as well as to hold the wafers. The electrode configuration is designed to provide a uniform plasma environment for each wafer to ensure that we are going to have a very much uniform deposition over the substrate. These vertically oriented graphite electrodes are stacked on a parallel to one or another side by side with alternating plates serving as a power and ground for the RF voltage, and this plasma is formed in a space between each pair of plate, right. So we have each pair of plate. Inside that we are going to have the wafer, and each pair at one end we are going to apply some supply, at the another end we apply some ground. Between that your glow discharge will be there, it will be created, that is used to that glow discharge is used for the deposition of the material. Okay. So here we have seen that we have this electrode, the another electrode, it is also used. See, we have this electrode and this electrode. sorry, this electrode and this electrodes. Here we have the wafers. Wafers will be placed here, and gas outlets. Gases will be inside from this side, and this way, with the help of this RF power input, we are going to provide some supply which will create the glow discharge, and the process will be carried out. Okay, and the another diagram here is the parallel plate type. We have this single wafer type. This is the parallel plate type. Parallel plate type reactor, and here we have the single reactor for the single wafer. Okay, so this is the reactor chamber. Some cooling material will be provided. Here we have the RF source. Okay, radiant heater will be there. Some quad windows will be there. Wafers are placed over this. Okay, see, we have the wafer. It is we have the single wafer, right? So gases will be provided inside the chamber. It will create a glow discharge, and then the process will be carried out. So this kind of chamber is used to for the deposition process of a very much large diameter, that is your 20 mm diameter. Okay, so that is why it is used as a single wafer for deposition process. Some safety issues are concerned in this deposition process, and most of the gases for the film deposition are toxic. These are hazardous and is not friendly with the environment. They can also cause the reaction with the vacuum pump oil, the oil which is used to create the vacuum. That pump also will have some oil, so it will react with that oil to give you the hazardous gas. So these gases are divided into 4 categories. First one is the pyrophoric gases that are flammable and explosive, poisonous gases, corrosive gases, and the dangerous combination of all these gases. So these gas combinations are here. These are the gases which we are going to have in the deposition process: ammonia, or argon, arsenide, dibromine, disilane, hydrogen chloride, nitrogen oxide, phosphine, silane. Oxygen, we know that it is a very much oxidizing. So these are the hazards which are going to have as per these gases, and we have some limits. Beyond that limit, these extraction of these gases is not acceptable, and the toxic limit particle per million is given in the table. So in this today's lecture, we have seen the deposition process, that what is deposition, why the deposition is required, what is the need of deposition, what type of material we can deposit, what type of reactors we are going to use. We have classified the deposition process in 2 parts. First one is your physical vapor deposition, and the another one is your chemical vapor deposition. So depending upon the material, we can have different type of reactors used, and the different type of deposition process can be used. So in the next lecture, we are going to see the chemical reactions and the temperature pressure range which are used for a particular material. For example, we are going to deposit polysilicon, silicon dioxide, or silicon nitride material. So in the next lecture, we are going to see which are the chemical reactions used for the deposition, and which type of reactor we are going to use. So thank you so much for today's lecture.